So, past a few things in wave mechanics by this time. We've learned a little bit about the mathematics involved, the parameters involved, and so on and so forth. What I'm going to introduce to you is what transpires subsequent to reflection of a wave. A wave traveling through a medium encounters a surface that separates it from another medium, and how it responds to that, what happens to the reflected wave. Now, to begin with, my focus would be reflection of transverse waves from the boundary separating it from another medium, right? Transverse waves traveling through a medium, encountering the boundary separating it from another medium, what happens? All right, this would be my subject of discussion for the next few minutes. So we have, let's say, a medium 1, and there is this medium 2. And this is the boundary, let's say a plane boundary separating the two media. All right. Now, from a wave perspective, we talk of a medium being rarer and denser. It's not related to the density of the medium. It's not related to the density of the medium. From the perspective of propagation of a disturbance, we define a medium to be rarer and denser. Suppose V1 is the speed of a wave in medium 1. V1 is the speed of a wave in medium 1. And V2 is the speed of the wave in medium 2. V1 is the speed of a wave in medium 1, and V2 is the speed of a wave in medium 2. If V1 is more than V2, if V1 is more than V2, if speed in medium 1 is more than speed in medium 2, then we say that medium 1 is rarer and medium 2 is denser. Then medium 1 is said to be a rarer medium, and medium 2 is said to be a denser medium. So, if you have to compare two media based on this, the medium in which the speed is less would be a denser medium. The medium in which the speed of a wave is less is going to be a denser medium. So, if V2 is more than V1, then medium 1 would be denser, right? In denser medium, the wave will travel with a smaller speed. In rarer medium, the wave will travel with a larger speed, right? That's how we define a rarer and a denser medium when we end up comparing two media, right? Now, so let's say there is a transverse pulse. There is a transverse pulse traveling through this medium. A transverse pulse traveling through this medium, and we call that pulse as an incident pulse. We call that pulse as an incident pulse. Let me describe this pulse. The pulse described by its displacement, right? Transverse displacement. If I'm talking of a transverse pulse, then these yi's are perpendicular to the direction in which energy propagates, right? So energy is propagating like this, and the displacements are transverse to the propagation of energy. So yi is, let's say, ai. Ai is the amplitude of the incident pulse, sine omega t minus k1x. K1 is the wave number for this medium. K1 is the wave number for this medium. And let's say K2 is the wave number, K1 is the wave number for this medium, which is like 2 pi by lambda 1. Lambda 1 is the wavelength in this medium. And K2, which is 2 pi by lambda 2. Lambda 2 is the wavelength in this medium. Now, one thing very cardinal. When a wave passes through a medium and is incident on a boundary separating it from another medium, part of the incident energy gets transmitted, part of the incident energy gets reflected, right? Transmitted or reflected. Transmitted or reflected. The frequency of the wave will not change. Frequency is something very fundamental, right? What came from the source then is adopted by the wave as its frequency. The frequency will not change on reflection or refraction. On reflection or refraction, transmission, frequency of a wave will not change. That means omega will remain the same. Omega is 2 pi n. Omega is angular frequency. 2 pi n. N will remain the same. N will remain the same. Right? So omega will also remain the same. However, wave velocity will differ. V1 will in general be different from V2. V1 in general would be different from V2, right? A larger V1 would mean a rarer medium, a smaller V1 would mean a denser medium, right? So one way or the other. So for sure, V1 is different. So V1 by N would be lambda 1, right? And V2 by N would be lambda 2. So very clearly lambda 1 and lambda 2 are different. And if lambda 1 and lambda 2 are different, the wave number K will be different. In general, K1 will be different from K2 because lambda 1 will be different from lambda 2, right? So this is an incident pulse, y equal to a sine omega t minus K1x. AI is the amplitude of the incident wave. And then part of the incident energy gets transmitted. Part of the incident energy gets transmitted, and in the process of transmission, what does not change? Omega. Omega and N will not change, right? So the transmitted pulse, YT say, is like AT. AT is the amplitude of the transmitted pulse. AT is the amplitude of the transmitted pulse. I am referring to this as the plus x direction. Let me say this is my plus x direction. So then AT sine omega t minus K2x, right? Right? That's the transmitted pulse. That's the transmitted energy. Now part of the energy will bounce back into the incident medium, right? So there is a reflected pulse. Now, switch it off. So there is a reflected pulse, right? This is an incident pulse and there is a reflected pulse. And the reflected pulse, YR, is traveling in the negative x direction, right? So its equation would be A reflected into sine omega t. Now K will remain the same because it's the same medium, so it will have K as K1 only. Sine omega t plus K1x. Sine omega t plus K1x. Yes or no? Right? Good. Now, in the incident medium then, what happens? In the incident medium, there is superposition of the incident and reflected pulse, right? However, in the transmitted medium, this is the only energy pulse. This is the only pulse traveling, right, in the transmitted medium. So, in the transmitted medium, Y2 is the same as YT. Why are the displacement profiles produced in medium 2, which is the same as what happens to the transmitted pulse? Y2 is the same as YT, which is like AT sine omega t minus K2x. However, in the incident medium, the displacement characteristics would be what? Yi plus yr. The displacement characteristics in medium 1, let me refer to that as y1. Let me refer to that as y1, the displacement characteristics in medium 1. And that's going to be ai sine omega t minus k1x plus ar sine omega t plus kx. That's a displacement profile produced in medium 1, k1x, right? Right, so eventually, what you see in medium 1 is this. What you see in medium 2 is this, right? And let me call this as x equal to 0. This boundary as x equal to 0. This boundary as x equal to 0, right? X equal to 0 belongs to y2, also belongs to y1. X equal to 0 is common between y1 and y2. So whatever is happening at x equal to 0, it should be possible to compute that either using this equation or using this equation. Both should give me the same value, isn't it? At x equal to 0, which is if I take a certain point P on x equal to 0, right? And I want to know at an instant of time t, what would be the displacement of P, right? Then I plug in x equal to 0 and I can plug in the value of time here to obtain what is happening at P at an instant of time t. Using this equation, because this point belongs to this medium, this point also belongs to this regime. Yes or no? I could have also obtained what's happening at P by plugging in x equal to 0 here. I would know what is happening at P from this equation. Now there should not be a contradiction between this equation and this equation, right? In some manner, these two equations should be friends at x equal to 0. At x equal to 0, whatever this gives me is what this should give me. Yes or no? Because x equal to 0 belongs to both. Both will take responsibility, equal responsibility for whatever is happening at any point P, which is x equal to 0. Yes or no? Clear? So, and you know, this fact, what I have stated qualitatively, the fact that I have stated qualitatively is mathematically referred to as continuity. Is referred to as continuity of the wave. Whatever I have referred to as very qualitatively is actually called continuity of the wave. In its passage from 1 to 2, it maintains dignity, it maintains continuity. It will not expose itself to any abruptness. That you know, this disturbance prevalent in medium 1 will show one kind of displacement for the particle P, whereas this disturbance traveling through medium 2 will reflect another kind of displacement characteristics for the same particle. They should be in sync with each other. Both y1 and y2 should be in sync with each other at x equal to 0, because that's their common framework. That's their common interface. That fact is called continuity of the wave. That fact is called continuity of the wave, right? Whatever I have said is actually referred to as continuity of the wave. Post x equal to 0 and prior to x equal to 0, there is no issue about continuity. Right? Only at x equal to 0, they will have to maintain continuity. Clear? Good. Now, essentially, this point P, is because of y1. That means y1 at x equal to 0 must be the same as y2 at x equal to 0, right? The value of y2 at x equal to 0 must be the same as value of y1 at x equal to 0. Right? What do I do when I say y1 at x equal to 0? It's an equation says what is the displacement this would have produced at the point P. Right? y2 at x equal to 0, what does that mean? It means what is the displacement that this would have produced at the point P. Both should have produced, right? Because it's the same wave continuing. In this medium, it shows up as y1. When it's passing on into this medium, it's showing up as y2. But at x equal to 0, they must give me the same number, the same output, the same value. Yes or no, right? So y1 at x equal to 0 is what? Plug in x equal to 0, that gives me ai sine omega t. This gives me ar sine omega t. ai sine omega t. This gives me like a ar sine omega t at x equal to 0. And what does this give me? At sine omega t. Yes or no? So which means I can cancel sine omega t from both sides and I end up getting ai plus ar as at. ai plus ar as at. Look, ai I know. What's my objective? I want to compute ar and at. ai I know. I have knowledge of the incident pulse, but I want to know of the amplitude of the reflected pulse. I want to know of the amplitude of the transmitted pulse, right? But this is just one equation. I need another one. I need another one, right? Look, again. There is a displacement profile passing from this medium to this medium. There is a displacement profile passing from this medium to this medium. At P, there is a y produced at P. There is a y produced at P at a certain instant of time. There is a slope of the tangent at P. There is a slope of the tangent at P. Right? Now the slope of the tangent at P, whether I compute using this equation or I compute using this equation, should give me the same value. Yes or no? The slope of the tangent at P, right? There is a displacement profile in its passage from this medium to this medium. There is a tangent at P that you could draw to the displacement versus x profile, right? The slope of the tangent at P, whether I obtain using this equation or I obtain using this equation, must be the same. Yes or no? Do you know what I'm saying? I should get the same tangent whether I use this equation or I use this equation. The tangent at P to the displacement versus x graph should be the same, right? That means, can I say dou y1 dou x is the slope of the tangent if I at x equal to 0 obtained from this equation? That's the slope of the tangent at P obtained using this equation. What's the slope of the tangent at P obtained using this equation? That must be dou y2 dou x at x equal to 0. Both refer to the slope of the tangent at P. And the two must be equal. The two must be equal. Yes or no? Clear? Good. So now, if I differentiate this with respect to x, what do I get? Minus ai k1 cos omega t minus k1x. Yes or no? Minus ai k1 cos omega t minus k1x. Right? And so minus ai k1 cos omega t minus k1x at x equal to 0 will simply be cos omega t at x equal to 0. You know what I did? If you differentiate this with respect to x, what do you get? Minus ai k1 cos omega t minus k1x. But the value of that at x equal to 0 would be what? Minus ai k1 cos omega t at x equal to 0. Right now? No? Okay, what about this? Plus ar k1 cos omega t. Differentiating this with respect to x and then plugging in x equal to 0. differentiating this with respect to x and then plugging in x equal to 0. That's the left hand side. Dou y1 dou x at x equal to 0. Is this yes or no? No? Nahi kya? Confused? Little confused? See, if I have to differentiate this, first of all, check this out. What is the derivative of y1 with respect to x? In general would be what? Minus ai k1 cos omega t minus k1x plus ar cos ar k1 cos omega t plus k1x, right? That's dou y1 dou x, differentiating y1 with respect to x. But I want derivative of y1 with respect to x at x equal to 0. So now if you plug in x equal to 0, what would you get? Minus ai k1 cos omega t plus ar k1 cos omega t, which is this, right now? And that must be the derivative of y2 with respect to x at x equal to 0. If you differentiate this with respect to x, what do you get? Minus at k2 cos omega t minus k2x. But at x equal to 0, what would it be? It would be minus at k2 cos omega t at x equal to 0. Yes or no? If you differentiate with respect to x, cos omega t minus k2x and then k2x with respect to x, chain rule, minus k2, right? Yes or no? That's chain rule, right? That's why you got a minus here also, because of this minus chain rule, right? Cos omega t goes away and I end up getting another equation, ai k1 minus ai k1 plus ak ar k1 equal to minus at k2. That's what I get. Yes or no? Two equations, two unknowns. I can solve for ar and at. Let's do that. If you allow me to remove all of this. So this at I can write as ai plus ar. To eliminate at can be written as ai plus ar in this equation. So let's see what I get. Minus ai k1 plus ar k1 equals minus ai plus ar k2. Yes or no? Replacing at by ai plus ar in this equation to solve for ar, right? So ar into k1 plus k2 equals ai into k1 minus k2, right? And ar then is k1 minus k2 divided by k1 plus k2 into ai. Yes or no? That's the amplitude of the reflected pulse in terms of the amplitude of the incident pulse ai. Yes or no? Very clearly, to obtain AT, what would you do? You have to add AI to AR. If you add AI to this, you'll get AT, right? So AT, amplitude of the transmitted pulse, is AI plus this, which is K1 minus K2 by K1 plus K2 into AI, right? That's the amplitude of the transmitted pulse. So that gives me AT equal to K2 will get cancelled. So 2K1 AI by A1 plus K1 plus K2. Yes or no? Do you understand what I did here? I solved for amplitude of the reflected pulse and amplitude of the transmitted pulse. In terms of amplitude of the incident pulse, given K1 and K2, the wave number of the two waves in medium 1 and medium 2. Yes or no? Can I remove this computation? This part? hey, look, lambda 1 is 2 pi by k1, isn't it? Lambda 1 is 2 pi by k1, right? So very clearly, k1 is, say, omega by v1, 2 pi n, which is omega by v1. Similarly, k2 is going to be omega by v2. K2 is going to be omega by v2. So I can write k1 and k2 in terms of speeds in the two medium, v1 and v2. Omega is the same for both the media. Omega will not change ever, right? So that gives me amplitude of the reflected pulse. Writing k1 as omega by v2, k2 as omega by v2, k1 as omega by v1, I end up getting v2 minus v1 by v1 plus v2 into amplitude of the incident pulse in terms of the velocities in the two medium, right? Replacing this k1 by omega by v1 and k2 by omega by v2, this is what I get, right? Similarly, amplitude of the transmitted pulse, amplitude of the transmit, k1 as omega by v1 and k2 as omega by v2, so that will become 2v2 by v1 plus v2 into amplitude of the incident pulse. Yes or no? In terms of the speeds in the two media? In terms of the speeds in the two media? Yes or no? Sounds good? Now the important thing is, have you finished making a note of this? Can I remove the clutter? Now, say if medium 1, this was medium 1 and this was medium 2. And say suppose this was rarer and this was denser. That means this is v1, velocity of this is v2. That means v1 more than v2, say. v1 more than v2. v1 more than v2. Now if v1 is more than v2, do you realize that this AR will become negative? AR will become negative, right? AR then would become negative. AR then would become negative, yes or no? Right? Now if AR is negative, what does it mean? That means when this goes from here to here, AR computed from this will become negative, right? So if it's negative, AR can be written as some minus AR, where AR is a positive number. Yes or no? Can be written as minus AR, where AR is a positive number. How about it? Right? Now what is YR? Y of the reflected pulse. Now I'm talking of a situation where the pulse is traveling from a rarer to a denser medium. V1 more than V2, rarer to denser. Speed and rarer will be more than speed and denser. So YR, which is the reflected pulse, right? This AR I write as minus AR, where small AR is a positive number. Small AR is the magnitude of the amplitude of the reflected pulse. Small AR is the magnitude of the amplitude of the reflected pulse, right? Right? So then this will become minus, replacing capital AR by minus AR, sine omega t plus k1x. Yes or no? Sounds good? See, all that I did is I wrote this capital AR as minus small AR, where small AR is a positive number, right? And this can be written as AR sine omega t plus k1x plus pi. This minus is taken care of by this pi, right? Sine pi plus theta would be minus sine theta, right? Yes or no? Which means what? Check this out. There is this incident pulse traveling in a rarer medium. This is an incident pulse traveling in a rarer medium, gets reflected from the boundary separating it from a denser medium. The reflected pulse is this. And do you realize that the incident pulse and reflected pulse differ in phase by pi? The incident pulse and the reflected pulse differ in phase by pi. Yes or no? That means there is a 180 degrees change of phase on reflection from a rarer to a denser medium. Write down. When a transverse pulse travels from a rarer to a denser medium, on reflection, it would undergo a phase change of 180 degrees or pi radians. On reflection, it will undergo a phase change of 180 degrees or pi radians. Also write down, physically, a 180 degrees change of phase, physically 180 degrees change of phase is 180 degrees change of phase is equivalent to an inversion of the incident pulse, you know what I'm saying? So on rarer to denser, when reflection occurs, then there is 180 degrees change of phase. What it means geometrically is that, this is what it means. See, suppose the incident pulse is like this. Say this is an incident pulse. The solid line is the incident pulse, right? Reflected pulse means there would be 180 degrees change of phase. That means 180 degrees change of phase of a pulse means inversion of that pulse. That means flip this pulse about the x-axis. When you flip this pulse about the x-axis, then this is what it would look like. The dotted line would be the inversion. That's 180 degrees change of phase. That's a reflected pulse. 180 degrees change of phase of a pulse means an inversion of the pulse. Reflect that pulse about its line of propagation. Reflect that pulse about its line of propagation. While a particle here, the incident pulse would have produced a crest, the reflected pulse for the same particle would have produced a trough. They would have been in their amplitude states, but opposite amplitude states about the mean position. This is the mean position, right? So wherever you would have seen a crest in an incident pulse, the reflected pulse would aim at producing a trough. Wherever you see a trough in the incident pulse, the reflected pulse would produce a crest. That is what is meant by an inversion. And 180 degrees change of phase does exactly that. 180 degrees change of phase does exactly that. Right? And when would 180 degrees change of phase take place? If this capital AR turns out to be negative. And when would capital AR turn out to be negative? If V1 more than V2. And when is V1 more than V2? If the incident medium is rarer compared to the denser medium. So reflection of a transverse pulse from a denser medium results in inversion of the transverse pulse. Reflection of pulse from a denser medium reflection of a transverse pulse from a denser medium, reflection of a transverse pulse from a denser medium results in inversion of the pulse, results in inversion of the pulse. Clear? And however, if V2 is more than V1, look at the case where V2 is more than V1. Okay, when I say V2 more than V1, then this would be denser, this would be rarer, isn't it? If V2 is more than V1, this is rarer, this is denser. Suppose this is denser and this is rarer. That means now if there is a pulse traveling in the denser medium and reflected from the rarer medium, a pulse traveling in the denser medium but reflected from the rarer medium, do you realize V2 more than V1, AR, capital AR will remain positive only? There would be no change of phase. There would be no change of phase. AR will remain positive and no change of phase takes place. No change of phase occurs in the reflected pulse if AR is positive. Only if AR is negative, there is change of phase. Only if AR is negative, there is change of phase by 180 degrees. But if AR is positive, then there would be no change of phase. There would be no inversion produced. That means now the incident pulse and the reflected pulse would be in phase with each other. Would be in phase with each other. You know what I'm saying? So, inversion occurs only if the traversal is from rarer to a denser medium. If reflection occurs from a rarer to a denser medium, then there would be inversion of, or flipping of the pulse. Clear? Sounds good? Now, let me also explain to you that there is a rigid support, and there is an incident wave, IW, incident wave, transverse pulse, and there is a fixed end, which is like a rigid support, Now, what happens is that if the incident pulse, let's say for example, if the incident pulse was like this, and say it was aiming at producing at this point an upward displacement of a certain kind, right? Then what should the reflected pulse do? The reflected pulse would do the following. Hey, this point has to be at rest because it's on a rigid support. It has to be at rest, right? If the incident pulse is aiming at moving this by a certain amount, then it's the job of the reflected pulse to pull it down by the same amount, so that there is no net displacement of this point, right? This is a fixed point. It's part of a rigid support. It cannot nudge, right? If the character of the incident pulse is to pull this point up by a certain amount, then the job of the reflected pulse would be to pull it down by the same amount, so that there is no net displacement of this point, And when can that happen? If the reflected pulse is an inversion of the incident pulse. That means if there is a phase change of pi. That means if reflection occurs at a rigid support. There would be no change of phase. I'm sorry, there would be 180 degrees change of phase. If an incident pulse is reflected at a rigid support or a fixed support, then there is going to be 180 degrees change of phase. There is going to be 180 degrees change of phase to maintain this point fixed. To maintain this point fixed. A 180 degrees change of phase would occur on reflection from a rigid or a fixed support. Also realize AT is always positive. AT is not becoming negative, right? So if AT is not becoming negative, the incident pulse and the transverse pulse are in phase with each other. That means transmission or refraction will never result in change of phase. Transmission or refraction will never result in change of phase, because the sign of AT is the same as sign of AI. AT is positive, as you can see, AI is also positive. Will never result in change of phase, whether the passage is from a rarer to a denser medium or a denser to a rarer medium. The transmitted pulse would be in phase with the incident pulse. Yes or no? Suppose, all good so far, right? Suppose there is a rigid wire of mass per unit length 4 mu, right? And there is another wire of mass per unit length mu, another wire of mass per unit length mu. And say there is a transverse pulse generated in this, and say this is my positive x direction. Say there is a transverse pulse traveling from mu to 4 mu. There is a transverse pulse traveling from mu to 4 mu. And let's say the transverse pulse traveling, that means this is a pulse traveling in the negative x direction. If this is the plus x direction, this is the pulse traveling in the negative x direction. Say the incident pulse is given by, say, 6 sine 40 plus, say, kx plus kx, right? This is the incident pulse. I want to be able to find the equation of the reflected pulse. I want to be able to find the equation of the reflected pulse. Say k I take as, say, 5x. Say 5x. K is 5, say. K is 5, say. All right. Now, first of all, velocity of a transverse pulse in a string. Now, this is one single unit, so tension will be the same everywhere. Tension will be the same everywhere. Let me call this incident medium 1. Let me call this transmitted medium 2. Right? Now, what's the velocity of wave in medium 1? God bless you. Is going to be square root of t by mu. Right? Did I derive this in the last class for you? Velocity of a transverse pulse in a string. Right? Root t by mu. Okay. What is the velocity of the transverse pulse in medium 2? Root t by 4 mu, which is half of V1. Do you realize half of V1? Which is half of V1? That means velocity in this medium is less than velocity in this medium. This must therefore be a denser medium. This therefore must be a rarer medium. This must be a denser medium. This must be a denser medium. This must be a rarer medium. Velocity here is less than the velocity there. Right? The velocity of the reflected pulse then is going to be AR, and the reflected pulse will travel in the positive x direction. Is going to be given by AR sine 40 minus kx minus 5x? Yes or no? Would be AR sine 4t minus 5x because it's in the plus x direction. I just need to compute AR. I just need to compute the amplitude of the reflected pulse going back in string 1. How do I compute AR? Using this. Using this. It will turn out to be a negative number very clearly. What is AI? AI is 6. What is AR? AR for this calculation is going to be replace V2 by half V1. V2 by half V1. So half V1 minus V1 divided by V1 plus half V1 into amplitude of the incident pulse. What's the amplitude of the incident pulse? 6. So which is like minus half divided by 3 by 2 of 6. That's going to be the amplitude of the reflected pulse, right? So that's like minus 2. Minus 2 would be the amplitude of the reflected pulse. So the equation of the reflected pulse is going to be minus 2 sine 4t minus 5x, which could also have been written as 2 sine 4t minus 5x plus pi. Could also have been written as 2 sine 4t minus 5x plus pi. Yes or no? That's the equation of the reflected pulse. How do you find the equation of the transmitted pulse? Hey, transmitted pulse and the incident pulse, both are traveling in the negative x direction. So the transmitted pulse would have what as its equation? The transmitted pulse could be written as y of the transmitted pulse is amplitude of the transmitted pulse sine 4t plus 5x, because the transmitted pulse also travels in the negative x direction. Omega remains the same. Hey, k changes. Yeah, I made a mistake. K will not be the same. It will not be 5x anymore, right? K will not be 5x anymore. K will change. In this case, for the reflected pulse, K was same. But for the transmitted pulse, it will not be 5x. It will be some K. Right? Right? K for the incident medium was what? K for the incident medium was 5. Right? Which is 2 pi by lambda for the incident medium. Lambda for the incident medium. Right? K for the reflected medium is going to be 2 pi divided by lambda in the reflected medium. Right? Right? All that you need to do is you need to divide this by this, right? K by 5, where K is the wave number in the transmitted medium, right? So K by 5 is going to be lambda r divided by, lambda I divided by lambda r. Yes or no? Lambda I divided by lambda r. Right? What is lambda I? Lambda I is velocity in the incident medium divided by frequency n. And what is lambda r? Velocity in the transmitted medium divided by n. V2 is half V1. We have computed V2 is half V1. So this becomes 2. Yes or no? We have computed V2 is half V1. Yes or no? This becomes 2. So then I get K by 5 is 2 and K therefore becomes 10. K therefore becomes 10. So replace this K by 10. That will be the equation of the transmitted pulse. That's going to be the equation of the transmitted pulse. Yes or no? So do you all understand the mechanism of reflection that occurs from a rarer to a denser medium of a transverse pulse and from a denser to a rarer medium of a transverse pulse, and what happens upon reflection from a rigid support? What happens on reflection from a rigid support?